This assignment is to analyze and test a simple dusk-to-dawn light, document your results, and recommend design changes if necessary. The dusk-to-dawn light simply uses a light sensor to turn a light on when the room gets dark and turn the light off when the room gets light. I'll provide an overview of the design and how it should work before demonstrating it in operation to show you how the data you'll be working with was acquired. Here's some context for the project. Someone at your company has come up with the bright idea to market a simple light which conserves energy by automatically shutting off when the room's lit by another source. The person who came up with the idea also came up with a preliminary design, but they need an engineer to do an official evaluation of the design. This is the preliminary design for our circuit. Now I'll discuss how this circuit is supposed to work and define some variables that we'll need later. This component is a bipolar junction transistor, which is generally abbreviated BJT. The BJT's terminals are the base, generally labeled with a B, the collector up here, which is called C, and the emitter down here, which is labeled with an E. Generally, it's assumed that the base current is approximately 0. The way we'll model this BJT's operation is as a voltage-controlled current source. That is, the collector current through here is set by the base to emitter voltage. Here. If V sub BE is small, no current flows through the collector and out the emitter. Generally, no current will flow if the base to emitter voltage is below about 0.7 volts. However, if you increase V sub BE above that value, the collector current also increases. So by increasing V sub BE, we can flow current from the collector and out the emitter. This component is a light-emitting diode, or LED. The diode behavior is controlled by the diode current and the diode voltage, V sub D. If V sub D is above about 2 volts, which implies there's sufficient current through the diode lights up. So if we increase the BJT base to emitter voltage sufficiently, we can flow current and light up this diode. This side of the circuit consists of a fixed 10 kilo ohm resistor and a photoresistor. The photoresistor's resistance changes with light level. To increase the base to emitter voltage of the BJT, we need to increase the base voltage of the BJT. The BJT base voltage is the same as the voltage across the photoresistor, this V sub B here. Since we're assuming that the BJT base current, this direction is 0, the current through the 10 kilo ohm resistor and through the photoresistor are both the same, and these two elements form a voltage divider. The photoresistor's resistance is high when the light level is low, and low when the light level is high. Therefore, the base voltage of the BJT should be high when the light level is low and the LED should turn on. Conversely, the BJT base voltage should be low when the ambient light level is high and the LED should turn off. Your job is to determine whether or not this circuit actually works as it's advertised to, and to make recommendations as necessary to improve the performance. You could probably just wire up the circuit and see if it works, but that's kind of a hobbyist's approach rather than an engineering approach. What engineers need to know is why it works, or why it doesn't work, or, most importantly, how you can make it work better. If you're going to answer those kind of questions, you have to first know how the components behave individually. Only then do you have a chance of understanding how the overall system works. First, I'll characterize the photoresistor. This one's easy. I just connect it to an ohm meter and measure the resistance under light and dark conditions. I'll do that now. This is our photoresistor. The resistance between these two terminals changes as I change the light level on the face of the photoresistor. To characterize our photoresistor, I'll connect its terminals to an ohm meter. At high light levels, I'm getting about 0.6 kilo ohms of resistance. If I cover it up under dark conditions, I'm getting more like 11 or 12 kilo ohms. Now I'll do the BJT characterization. I'll get the collector current, I sub C, as a function of the base to emitter voltage, V sub BE. First, I'll show a schematic of the circuit we'll use to measure that relation, then we'll do our demo. The proposed design has a collector voltage of 6 volts, so I'm going to use a voltage source to apply 6 volts to the collector here. This resistor limits the current in the circuit so we don't blow anything out. A function generator will be used to apply various values of V sub BE, and an ammeter up here will measure the corresponding collector current. Now I'll show you the physical circuit and demonstrate the data acquisition. Here's our BJT. It has 3 terminals. This is the collector, this is the base, and that's the emitter. Here's our circuit to characterize the BJT. This is a little battery pack containing 4 AA batteries. It applies 6 volts between the collector and the emitter. I've got an ammeter between the positive terminal of the battery and this terminal of the 47 ohm resistor to measure current into the collector. I'm using this DMM to measure the base to emitter voltage, and I've got a waveform generator, the yellow and the black wires here, set up to apply a base to emitter voltage across the BJT. At the moment, I've got 0 volts applied between the base and the emitter, and we have no current through the BJT. If I change that, let's increase that voltage to about 0.5 volts. So now I've got 0.5 volts, I'm still not getting any current. If I increase this voltage to about 0.7 volts, I should start flowing current. So at 0.7 volts, I'm getting about 3 milliamps plus a little bit more. Increasing that voltage to say 0.8 volts increases the current to 37 milliamps. As I continue to increase this to say a volt, I'm up to about 110 milliamps. So increasing the base to emitter voltage increases the current through the BJT. Finally, you need to characterize the LED. That can be done by testing it, but it's probably time you looked at some data sheets. So do some searching on the internet to see what you can find out about voltage and current levels for the LED operation. Now that we have some idea of how the components work, let's finally construct the dusk to dawn light and see how it works. Remember, you don't just want to decide whether the circuit works or not. You need enough information to decide how it works and whether it can be made to work better. This is our final dusk to dawn light circuit. This is our fixed 10 kilo ohm resistor. This is our photoresistor. We've used this same battery pack to apply 6 volts across these 2 terminals. This terminal is connected to the base of the BJT. We also have 6 volts connected to the BJT's collector. The emitter of the BJT is connected to the LED, which is also grounded. Under light conditions, the LED is off. If we turn off the lights in the room, the LED turns on.